Okay, everyone, back to alcohols. We're going to talk about the reactions of alcohols in this next part of chapter 8. So let me go ahead and share my screen. And get rid of me. All right. So alcohols can react with active metals. So when I have metals like lithium or sodium or potassium, remember these are group 1A, and they're very, very reactive. What happens is the metal is reacting with the alcohol and actually liberating hydrogen gas and forms a metal alkoxide. So this is sodium methoxide. I can also use ethanol and get sodium ethoxide. Remember, these are really important nucleophiles and bases in my substitution and elimination reactions. Alkoxides are very strong. They're generally stronger bases than OH minus. They can also be used as nucleophiles in my nucleophilic substitution reactions. They can be used as bases in my beta elimination reactions. So this was all chapter 7, materials. And if you ever wondered, well, how do I get that sodium ethoxide or sodium methoxide? This is how I take the alcohol and I react it with a very highly reactive metal. And what I have is an oxidation reduction reaction, and I end up with the ethoxide and H2 gas, which bubbles away. Now, I can also convert alcohols to alkyl halides. Water-soluble tertiary alcohols. So to be water-soluble and tertiary, I have to have pretty low molecular weight in general. These are going to react very rapidly with hydrochloric acid, HBr, HI, and this can happen at room temperature. And what I'm going to go is I'm going to substitute the halogen for the OH. Low molecular weight primary and secondary alcohols are unreactive. They do not react under these conditions. I actually go through the tertiary carbocation. The hydrogen will protonate. That water will leave to give me the primary or the tertiary carbocation, and then the Cl is going to come in and actually form that nucleophilic bond. So because my tertiary carbocations are so stable, these tertiary alcohols are going to be able to do this. The low molecular weight primary and secondary alcohols are not, because those carbocations are not very stable. I can also take water insoluble tertiary alcohols, and I can react by bubbling gaseous HCl through the solution of the alcohol, and I dissolve this in diethyl ether or THF, so an unreactive solvent, and I can also do this substitution. This will also go through my tertiary carbocation. First I have protonation, then I have loss of leaving group, and then the Cl minus is going to come in and react with the carbocation. Again, this is very, this is review, basically. We've talked about this in chapter 7. Now, to get primary and secondary alcohols to react in this way, I need concentrated HBr and HI. And then I will get a reaction to occur, and I can form alkyl bromides and iodides under these conditions with primary and secondary alcohols. So let's look at this reaction. Tertiary alcohols react with HX by an SN1 mechanism. I alluded to that briefly. The first step is to add a proton, right? This is nucleophilic. It's an area of electron density. This is the electrophile. It's got a partial positive. It's electron poor, right? I have this protonation of the OH group, and the purpose of this is to convert it to the better leaving group. OH minus is not a good leaving group, but if I take this and I actually attack the hydronium ion, remember HCl plus water is going to give me H3O plus Cl minus. So this hydronium ion is in solution under these conditions, and then I have my Cl, which is going to act as a nucleophile later. So these electrons come out on the water. What I'm doing is I'm getting an oxonium ion and then neutral water. This now is a better leaving group because it is a neutral atom or a neutral molecule that actually leaves. So this converts the leaving group from OH minus, which is a very poor leaving group, to neutral water, which is a much better leaving group. So step 2, the leaving group leaves. I break a bond to form a stable molecular ion. So the leaving group is going to leave. Those electrons are coming with it. What I get is my tertiary carbocation, and then I get neutral water. So now this water molecule is a much better leaving group because it leaves as a neutral water molecule. So that is much preferred to OH minus leaving. The third step then is the reaction of an electrophile and a nucleophile to form a new covalent bond or a nucleophilic attack, because my Cl minus, which was present based on this reaction I alluded to before, is now coming in to form that new covalent bond. My Cl has replaced my OH, and what I ended up is making this tert-butyl chloride, or the 2-chloro-2-methylpropane. It's actually a lot easier to call it tert-butyl chloride in these conditions. So this is a mechanism that is very reminiscent, or hopefully it is, of what we've discussed in SN1 reactions in chapter 7. So again, this is basically review, and you do need to know how to write this mechanism out. Now, if I have a primary alcohol, I react by an SN2 mechanism. Remember, my primary carbocations are unstable and they will not react. So let's look at this reaction. The first step is still protonating the alcohol. I have my nucleophile, right? I have my electrophile. This is an area that's electron rich. This is an area that's electron poor. This is also sort of an acid-base reaction. If this is the base and this is the acid. So my lone pair are going to attack the hydrogen, and then what I have is an oxonium ion. Now this is also a better leaving group because now it's a neutral ion that's going to leave. But instead of having the leaving group leave to form a carbocation, this next step is simultaneous and concerted, right? So this is a concerted reaction now. My nucleophile comes in and my leaving group leaves all in one step. So this is a concerted simultaneous bond making, bond breaking step, which is what characterizes the SN2 reaction. And now I have this primary alkyl bromide as a result. So again, this should be review. There's nothing new here. When I have alcohols, though, the one thing you have to remember is that they are typically going to protonate to form better leaving groups before they will undergo these substitution reactions. So just like we talked about before, the reactions are governed by a combination of electronic and steric effects. If I have a primary alcohol, it'll never react by SN1. It will only react by SN2. If I have a tertiary alcohol, this will never react by SN2. It'll only react by SN1. This is the one, that secondary alcohol, that I have to really figure out if the steric factors or the electronic factors are going to dominate or predominate in this by analyzing the conditions of the reaction, just like we did in chapter 7. All right, this is a new reaction with a new reagent. This SOCl2 is called thionyl chloride. It kind of looks like this. And let's see, I have 6, 8, 14, which is 22. Wait, 7 plus 7 is 14, plus 6 is 20, plus 6 is 26. So 2, 4, 2. I think it's got another lone pair there. But it basically looks like this. I'd have to check that. I have to do it quicker than just 2 seconds in my head. What you get with this is, in the presence of pyridine, which is an aromatic base that looks like that, I end up having a alcohol, a primary alcohol going to a primary alcohol in one stop. What I end up with is sulfur dioxide and HCl. This actually reacts with the pyridine, and I get this pyridinium chloride, which sort of takes this strong acid out of the equation. But this is another reaction. This is very widely used for converting primary and secondary alcohols to alkyl chlorides. Sometimes the SN2 reaction is harder to do depending on what else I have around. I can't do an SN1, so thionyl chloride is a very good way of taking this alcohol and converting it to the chloride, since this is thionyl chloride. Now, remember, I can also dehydrate alcohol, right? The alcohol can be converted to an alkene by beta elimination, also chapter 7 material. So I can eliminate a hydrogen and an OH. Basically, I'm eliminating water, hence the dehydration, right? For this to happen with primary alcohols, I have to have this alcohol heated at very high temperatures, and I have to have an acid catalyst like sulfuric acid or phosphoric acid. Secondary alcohols will undergo dehydration a little easier, so I can have some lower temperatures. Tertiary alcohols, basically you can look at them wrong, and if they have a little bit of acid around, they're going to go ahead and do this dehydration. So my temperature is only at or slightly above room temperature when I'm doing this. And again, this is going to be a dehydration. I'm losing water. So here's some examples. If I have ethanol, I'm losing water and I form ethylene. If I have cyclohexanol, I'm losing water and I form cyclohexene. Here, I can lose water and I can take any one of these hydrogens. Those are all beta hydrogens, they're all equivalent. And what I'm gonna get is this 2-methylpropene. Again, this should be review, as we did cover this when we were talking about beta elimination reactions in chapter 7. Now, remember, when isomeric alkenes are obtained, the more stable alkene, which is the one that is the most substituted, is going to predominate. Remember, this is called Zaitsev's rule. So here I have my OH. I have a hydrogen on this, and I have a hydrogen here. I can eliminate in this direction or this direction. Notice I get 80% of this 2-butene because this is di-substituted. So this alkene is more stable. And then this is the least substituted. It's only monosubstituted, which is less stable. So following Zaitsev rule, you're going to get this as the major product. And you always have to consider regiochemistry, right? This is an example of regiochemistry. And now that you are highly sophisticated organic chemists, you do always have to look at, well, what's the regiochemistry going to be? What's the stereochemistry going to be? What is the chemistry, which is pretty all-encompassing of what's happening in this particular reaction under these particular conditions. So remember, we always have to start thinking at the whole picture when we're starting to develop our chemistry skills. So it's not just a one-shot, oh, I have to memorize this. Honestly, you have to understand what's happening based on the chemistry, and then everything else falls into place. So let's look at this dehydration of a secondary alcohol. If I have some acid, right, whatever acid I have plus water is going to give me this hydronium ion, which is always, if I have acid and water, this is what I'm getting. And that's going to be my electrophilic species. So again, I have a proton transfer step, right? This is going to be attacking the hydrogen. This bond is breaking. This bond between the oxygen and the hydrogen is forming. So this is forming, and these electrons are what broke in the H3O+. I do get this positively charged oxonium ion species. Remember, this is a good leaving group, but now what's going to happen is I am going to break a bond to form that stable molecule, or I have loss of leaving group. So this is going to go ahead and leave as a neutral molecule. I end up with my secondary carbocation. And then remember what carbocations can do. They can rearrange, They can form a new covalent bond by reacting with a nucleophile, or they can eliminate. Carbocations can do any one of those three things. Here, my water is acting as the base. Even though it's a weak base, it's still a base. This is my alpha carbon, this is my beta carbon. These electrons are going to go ahead and pick off that hydrogen. The electrons that were in that bond are going to go toward the carbocation. So what I'm going to do is form this new bond, which is that double bond. And then I start off with my hydronium ion, which is regenerated. So this is actually a catalytic reaction. I only need a small amount of acid to keep this reaction propagating. Now, if I have the dehydration of a primary alcohol, remember, I'm not going to form a primary carbocation, but I will undergo E2 reaction, right? The first step is going to add a proton because I have to make a better leaving group, right? So I have to have this acid around so I can protonate the alcohol and form this oxonium ion. And then in my concerted simultaneous bond making, bond breaking step, right? This is still acting as the base. This is going after, this is the alpha, this is the beta, this comes in, this bond breaks. So what I have is reaction that happens together. I regenerate the acid catalyst and I form the alkene, which is the product of the beta elimination. So this is undergoing an E2 reaction where everything is concerted. I have simultaneously bond making and bond breaking. And remember, that's because under these conditions, I can't form a primary carbocation. So I do undergo a different type of mechanism. Now, it should be noted that acid catalyzed hydration, which is what we've been talking about, and dehydration of the alcohol are competing processes. So these are reversible reactions, right? I can go in this direction or I can go in this direction. This will be the rules of equilibrium and Le Chatelier's principle are going to dictate which type of process is going to predominate. If I have large amounts of water, right, if I increase the amount of a reactant, I am going to shift away. I'm going to shift right to the product side according to Le Chatelier's principle. That's going to favor alcohol formation. If I sort of somehow reduce the ability, take water out, or I don't have very much water around, that's going to go ahead and shift things to the left, which is the alkene side. So I can choose conditions in order to favor either the forward reaction, which as written is the hydration of the alkene, or the reverse reaction, which is as written the dehydration of the alcohol, by choosing appropriate conditions. Another key reaction of alcohols is oxidation. When I have a primary alcohol, I can get an aldehyde or a carboxylic acid. And this is going to be dependent on the strength of the oxidizing agent and any experimental conditions. Now, it should be important to note that oxidation of secondary alcohols are always going to give ketones. There's no choice there. It's only with the primary that I either get the aldehyde or the carboxylic acid, depending on conditions. So keep that in mind. The most common oxidizing agent is chromic acid. This is generally formed when I take this chromium 6 oxide in the presence of water and H2SO4. I make chromic acid. This is also called Jones reagent. And this is a very, very strong oxidant. So here's what I'm going to look at. When I have a primary alcohol, under these conditions, the primary alcohol is going to first go to the aldehyde. Remember, oxidation is also loss of hydrogen. And here I'm losing H2, right? This is minus H2 in order to form the aldehyde. And oxidation is also addition of oxygen. So here I've added an oxygen between that carbon and the hydrogen of the aldehyde, and I end up with a carboxylic acid. Carboxylic acid. Now, notice that I really can't stop here. This is an intermediate. This is what these brackets means. As sort of an intermediate. It's sort of not something that is going to be isolated very effectively, because once it forms, it's going to further oxidize. So when I use Jones reagent or this chromic acid, primary alcohols will not stop at the aldehyde and will go completely to the carboxylic acid. Now, if I have a secondary alcohol, I will get a ketone. But primary alcohols do something a little bit different. Now, if I want to stop this primary alcohol and I want to isolate an aldehyde, I have to use a different set of conditions. This is one such set of conditions. I have something called pyridinium chlorochromate. It's very commonly referred to as PCC. This is what it looks like. So note that this is PCC. This is the structure of it. I have a pyridinium, so I have a quaternary nitrogen with this chlorochromate ion. So it's called pyridinium chlorochromate. It is obtained by reacting pyridine with HCl and also that same thing as I have here, that chromium 6 oxide. So what I get though is I get formation of this aldehyde and then it stops. I can get aldehyde specifically by oxidizing primary alcohols with PCC. So this is a selective way to make the aldehyde. The aldehyde will not further oxidize to form the carboxylic acid. It should be important to know that tertiary alcohols are not oxidized by anything. Notice that if I have a tertiary alcohol, because these are all carbon groups, I can't form a carbonyl, right? I can't do that. So I can't, there are no conditions to go from a tertiary alcohol to a anything else. So primary alcohols will oxidize to aldehydes and then to carboxylic acids using chromic acid. Primary alcohols will oxidize to aldehydes using PCC, and that is the product that I isolated. Secondary alcohols, I can use chromic acid or PCC, and I'm going to get a ketone, and then my tertiary alcohols do not oxidize by anything. So that is what you need to know about oxidation. So I just want you to show when I have a secondary alcohol, notice it's these two hydrogens, right, that are going to be lost. Remember, oxidation is loss of hydrogen. And then I end up with this RR, right? So this would be the ketone. So make sure you understand these differences, because these oxidation reactions are really prevalent in organic chemistry and an important way to manipulate functional groups. I can go from an alcohol to a ketone, an alcohol to an aldehyde, an alcohol, if it's primary, to the carboxylic acid. And I'm limited with what I can do with tertiary alcohols. So all of that should be known. At this point, we're done with the reactions of alcohols. I will be back later in order to continue discussing the rest of these guys. I think next we're going to look at ethers, and then we're going to look at thiols, and then that will be the end of this chapter, and we'll continue on to the next. But anyway, I will see you soon.